Welcome to Civil Engineering Edge, your destination for deep insights into the world of infrastructure, innovation, and futuristic engineering. In today's video, we're diving into one of the most astonishing possibilities of future urban development mega underground cities. Imagine entire districts, homes, transport hubs, industries, farms all built beneath the Earth's surface. Why are engineers exploring downward instead of upward? What technologies make this even possible? And could underground cities become humanity's next great frontier? Stay tuned as we break down the engineering, the challenges, the innovations, and the future of living below ground. Let's begin. Imagine a city, not sprawling across land, but burrowing deep beneath it. What if our future isn't in skyscrapers, but in subterranean megadevelopments? Get ready to dive into the astonishing engineering and surprising technologies making these underworld cities a very real possibility. The intricate planning and construction of massive underground urban developments is explored. The surprising technologies and engineering feats required to create subterranean metropolises are unveiled. The subterranean allure. Why go underground? As cities grow denser and land becomes scarce, engineers and planners are forced to rethink the very idea of urban expansion. Instead of competing for limited surface space, visionary thinkers are now looking downward toward the vast, untapped world beneath our feet. The concept of constructing entire districts, transit networks, and public facilities underground isn't just science fiction. It's becoming an urgent solution to modern challenges, from mitigating climate extremes to protecting populations from natural disasters. Subterranean development offers safety, sustainability, and long-term resilience. Underground spaces have stable temperatures, reduced exposure to environmental hazards, and immense potential for innovative design. With advanced excavation technology and groundbreaking materials, the once impossible idea of underground cities is fast evolving into a practical engineering frontier. This section explores why the future of urban life may not rise into the sky, but instead descend into intelligently designed, climate-shielded environments deep below the surface. The pressing realities of surface overpopulation and extreme climate events pushing humanity underground. Rapid population growth has pushed major cities into a crisis of space, affordability, and sustainability. Urban areas, especially megacities, are running out of buildable land, forcing millions of people into congested neighborhoods where housing density and infrastructure stress have reached dangerous highs. This growing surface-level pressure demands new solutions, and engineers are increasingly considering the underground realm as a viable alternative. The ground below provides enormous, underutilized volumes that can be transformed into safe, climate-resilient habitats. In addition to overpopulation, extreme climate events are accelerating the need for such alternatives. Rising temperatures, stronger hurricanes, relentless heat waves, droughts, wildfires, and severe flooding are making many surface environments increasingly hostile. Coastal cities face chronic inundation risks as sea levels rise, while inland cities struggle with heat islands and water scarcity. Underground spaces, naturally insulated from weather fluctuations, offer stable temperatures year-round and protection from storm surges, wildfires, and thermal extremes. By relocating essential facilities, transit hubs, storage systems, and even residential zones beneath the surface, cities can safeguard populations from environmental instability. Moreover, underground development reduces the pressure on existing land resources, preserving green areas and enabling more sustainable city planning. For nations facing both rapid urbanization and climate threats, subterranean urban expansion represents not just a futuristic concept, but a practical necessity. As climate risks intensify, the underground is becoming humanity's most reliable refuge, a strategic response that combines engineering innovation with climate adaptation to protect future generations. historical precedents, ancient cave dwellings to modern bomb shelters, showcasing our primal instinct for subterranean refuge. Humanity's fascination with underground living isn't new. From prehistoric times, people have sought shelter in caves to escape extreme weather, predators, and conflict. These natural formations provided stable temperatures, security, and a sense of protection that open landscapes could not offer. Ancient underground settlements, such as Durinkyu in Turkey, a vast multi-level city carved entirely below ground, reveal the remarkable ingenuity of early civilizations. These subterranean labyrinths housed thousands of people, complete with ventilation shafts, storage rooms, water wells, and communal spaces. They served as strategic refuges during invasions and environmental hardships. In China, millions lived in Yaodong's earth-sheltered cave homes valued for their thermal comfort and energy efficiency. Fast forward to the 20th century, and underground spaces took on new significance during wartime. Massive bomb shelters, metro tunnels, and underground bunkers were constructed to protect civilians from aerial attacks. Cities like London, Moscow, and Berlin relied heavily on subterranean networks as safe havens during conflict. Throughout history, this recurring return to the underground reflects a deep-rooted instinct, the need for safety, stability, and survival. Even in modern times, data centers, military bases, research facilities, and archives are often built underground for enhanced security and climate control. These historical precedents demonstrate that humans have always understood the protective advantages of subterranean environments. Today's push toward underground megacities builds on this ancient legacy, combining timeless principles of refuge with cutting-edge engineering to create sophisticated, resilient urban spaces, teasing the extraordinary benefits and unseen potential of living beneath our feet. Underground living unlocks a world of possibilities that go far beyond simply creating more space. Beneath the surface lies an environment with unique characteristics that can be engineered into extraordinary advantages for future cities. Temperature stability is one of the biggest benefits. Underground spaces naturally maintain cooler conditions in summer and warmer conditions in winter, significantly reducing energy consumption for heating and cooling. This creates opportunities for ultra-efficient buildings and eco-friendly infrastructure. Subterranean cities also shield residents from noise pollution, air pollution, and extreme weather events, offering unparalleled environmental control. Deep below the surface, designers can craft immersive, human-centric environments using smart lighting systems that simulate daylight, natural landscapes, and relaxing ambiences. The underground also presents massive potential for expanding transportation networks without disrupting surface life. High-speed tunnels, automated logistics corridors, and multi-level transit hubs can operate seamlessly beneath bustling cities. Sustainable resource loops such as underground hydroponic farms, advanced water recycling facilities, and waste-to-energy systems can create self-sustaining ecosystems that operate independently from surface limitations. The geology of underground spaces also provides exceptional protection for sensitive installations like data centers, laboratories, and emergency shelters. As technology continues to advance, the unseen potential of subterranean development becomes increasingly clear. These environments can become quieter, greener, safer, and more efficient than many surface cities. The future underground city isn't just a backup plan, it's a bold opportunity to reimagine urban life with innovation, resilience, and sustainability at its core. Unearthing the impossible, mega engineering challenges. Building massive underground cities is an engineering ambition unlike anything humanity has attempted before. While surface construction deals with open space and accessible terrain, subterranean development demands confronting the Earth itself, creating vast caverns, multi-level transit systems, and habitable districts deep underground requires overcoming extraordinary technical, geological, and human-centered challenges. Engineers must work with limited visibility, high ground pressure, unpredictable rock formations, and groundwater intrusion, all while ensuring structural safety for thousands of residents. Beyond excavation, designers must account for ventilation, emergency access, fire safety, waste removal, and long-term maintenance in a closed environment. The psychological comfort of people living underground also becomes a critical factor. These mega-engineering tasks push current technologies to their limit, inspiring new innovations in drilling, reinforcement materials, and automated construction. This section explores the monumental hurdles faced by engineers and the cutting-edge solutions that make these underground dreams plausible. The colossal task of excavation. From advanced tunnel boring machines to innovative rock melting technologies, excavating the enormous spaces required for underground cities is one of the most daunting engineering tasks imaginable. Traditional methods like drilling and blasting are too slow, disruptive, and imprecise for creating large, interconnected subterranean districts. This is where modern tunnel boring machines TVMs revolutionize construction. These massive mechanical giants, sometimes hundreds of meters long, can cut through rock with remarkable precision, while simultaneously installing tunnel linings to stabilize the excavation. TVMs reduce surface disruption, increase safety, and enable continuous, high-speed tunneling. However, even TVMs face limitations when dealing with extremely hard rock, mixed ground conditions, or the need for massive cavern formations rather than simple tunnels. To overcome these challenges, researchers are exploring futuristic excavation technologies such as plasma drilling and microwave rock melting systems. These emerging methods aim to soften or liquefy rock using intense heat, allowing excavation without contact-based cutting tools. This could dramatically accelerate construction while minimizing tool wear and geological disturbance. Other innovations include robotic mining systems, autonomous drilling rigs, and AI-powered geotechnical mapping that predicts rock behavior in real time. Engineers are also experimenting with using controlled chemical expansion agents, 3D rock fracturing patterns, and advanced hydraulic cutters for shaping enormous caverns with high precision. As underground developments expand in scale, excavation will continue to evolve into a blend of mechanical, thermal, and digital technologies working together. The future of subterranean construction depends on mastering these groundbreaking excavation methods, pushing the boundaries of what is possible beneath the Earth's surface. Mitigating geological risks, seismic activity, water infiltration, and the stability of massive cavernous structures. Building large-scale underground spaces requires an intimate understanding of geology, since the Earth itself becomes the structural envelope of the city. Geological risks, such as seismic activity, pose significant challenges. Underground structures must be engineered to withstand ground shaking, stress redistribution, and potential rock fracturing. Although underground environments naturally experience lower seismic forces compared to surface buildings, improper design can still lead to collapses or tunnel deformation. Engineers address this by using flexible joint systems, shock-absorbing linings, and real-time monitoring instruments embedded in the rock. Water infiltration is another major risk. Groundwater can seep into tunnels, increase soil pressure, or cause flooding if not carefully controlled. Waterproof membranes, multi-layer sealing systems, and deep-well dewatering technologies are essential for ensuring long-term dryness. In high water pressure zones, engineers may use ground freezing techniques or chemical grouting to stabilize soil and block water pathways. Stability of large caverns presents its own set of difficulties. The bigger the open space, the more stress concentrates around its boundaries. Engineers rely on rock bolts, reinforced linings, steel ribs, and fiber-reinforced shotcrete to maintain structural integrity. Advanced simulations help predict how rock masses will behave when excavated, preventing unexpected collapses. Continuous geotechnical monitoring using sensors, laser scanning, and seismic imaging is crucial for detecting early signs of movement or instability. Addressing geological risks isn't just a technical necessity, it ensures the safety, longevity, and sustainability of underground developments. These solutions demonstrate how geological science and engineering expertise converge to create stable subterranean megastructures. Overcoming the psychological barriers of subterranean living, light deprivation, and claustrophobia. Even if underground spaces are engineered perfectly, human psychology remains one of the most influential factors in their success. Living beneath the Earth's surface challenges our natural desire for sunlight, open horizons, and a sense of spatial freedom. Light deprivation is a major concern because natural daylight plays a vital role in regulating circadian rhythms, mood, and overall mental health. Engineers and designers tackle this by integrating advanced lighting technologies such as full-spectrum LEDs, tunable smart daylight systems, and fiber-optic skylights that channel real sunlight from the surface. These artificial skylights can simulate sunrise, sunset, and varying daylight tones to create a more natural ambience. Claustrophobia is another barrier, especially in enclosed underground environments. To counter this, designers focus on creating spacious interiors with high ceilings, wide corridors, and visually open layouts. Architectural features like mirrored surfaces, curved walls, and panoramic digital screens can create the illusion of expanded space. Nature integration also plays a crucial role. Indoor gardens, green walls, water features, and biophilic design elements help reduce stress and provide a sense of connection to the natural world. Community spaces, recreational zones, and sensory-friendly lighting further enhance comfort. Psychological experts are increasingly collaborating with engineers to study behavioral responses to subterranean living. Through thoughtful design, immersive technology, and environmental engineering, the emotional challenges of living underground can be transformed into unique, engaging experiences. With the right innovations, underground cities can feel not only comfortable but deeply inspiring. Life below the surface, innovating for subterranean cities, creating livable underground cities goes far beyond excavation and structural engineering. It requires reimagining how humans experience their environment. Life below the surface demands careful innovation in air quality, lighting, food production, waste systems, community design, and psychological comfort. Engineers and architects must replicate the essentials of natural environments: fresh air, greenery, daylight, and acoustic balance within enclosed subterranean spaces. This means designing advanced ventilation systems, artificial skylights, sustainable ecosystems, and interactive public spaces that eliminate the feeling of confinement. Technological breakthroughs in urban farming, recycling, and energy generation allow underground cities to become more self-sustaining, reducing dependence on surface resources. These innovations work together to create communities that are not only functional, but pleasant, healthy, and inspiring. This section explores the cutting-edge techniques that make deep Earth living possible, transforming underground megastructures into thriving, human-centered habitats equipped to support long-term life. Revolutionizing air circulation and purification to mimic natural environments. Air quality is one of the most critical factors in making underground cities livable. Without natural wind, atmospheric exchange, or exposure to fresh air, engineers must develop systems that reproduce the freshness and purity of outdoor environments. Modern subterranean ventilation relies on multi-stage air circulation systems that integrate mechanical ventilation, natural air shafts, and advanced filtration technologies. These systems continuously supply oxygen-rich air while removing carbon dioxide, moisture, and pollutants. High-efficiency particulate air HEPA filters, activated carbon filters, and photocatalytic oxidation units help purify the air by eliminating dust, microbes, chemicals, and odors. To mimic the feeling of natural breezes, some designs incorporate variable airflow patterns and gently fluctuating air speeds, replicating the dynamics of outdoor wind. Environmental sensors monitor air composition in real time, automatically adjusting ventilation rates to maintain comfort and safety. For deep underground zones, engineers use air pressurization techniques to prevent stale air pockets and promote circulation through long tunnels and large chambers. Additionally, vegetation plays a key role. Green walls, indoor gardens, and biofiltration systems help absorb carbon dioxide and release oxygen naturally. Innovations such as artificial sky gardens combine plants with controlled sunlight simulation to enhance oxygen production. Through these advanced technologies, underground spaces can achieve air quality equal to or even better than surface environments. The goal isn't just to supply breathable air, but to create an atmosphere that feels natural, refreshing, and uplifting for those living and working below ground. **3 be pioneering self-sustaining ecosystems for food production and waste management deep underground. To support long-term habitation, underground cities must incorporate ecosystems capable of producing food and processing waste without relying heavily on surface infrastructures. Advances in vertical farming, hydroponics, aquaponics, and aeroponics are making this possible. These systems allow crops to grow in stacked layers using nutrient-rich water solutions instead of soil, drastically reducing space and resource consumption. Artificial lighting using full-spectrum LEDs replicates sunlight, enabling year-round crop growth regardless of external weather conditions. Underground farms can cultivate vegetables, fruits, herbs, and even protein sources such as fish or insects through closed-loop aquaculture systems. Waste management is equally important. Modern underground ecosystems utilize anaerobic digesters, composting reactors, and biogas plants to convert organic waste into useful outputs like fertilizer, methane gas, and nutrient-rich water. Greywater recycling units treat wastewater for reuse in irrigation or toilet flushing, while advanced filtration systems convert black water into clean, reusable water. By integrating waste to energy systems, underground cities can generate electricity and heat through biomass conversion processes. These interconnected systems form circular resource loops where byproducts from one process become inputs for another. The result is an efficient, sustainable ecosystem that minimizes resource dependency and reduces environmental impact. Such innovations allow subterranean settlements to function almost autonomously, enhancing their resilience in the face of climate change, supply chain disruptions, or surface-level disasters. Creating these closed-loop systems is essential for making underground living not just possible, but sustainable on a long-term, city-wide scale. **3 designing human-centric spaces, integrating virtual skylights, green walls, and advanced acoustics for comfort. Human comfort is at the heart of successful underground city design. To counter the lack of natural sunlight, engineers incorporate virtual skylights, high-resolution LED panels, or fiber optic systems that replicate real sky views, complete with moving clouds, changing colors, and day-night cycles. Some systems channel actual sunlight from the surface using mirrors and light tunnels, bringing genuine daylight deep underground. Green walls and indoor landscapes play a major role in enhancing psychological well-being. These planted surfaces purify the air, add natural beauty, and reduce stress by simulating outdoor environments. Large underground atriums, biophilic corridors, and botanical hubs help residents feel connected to nature even without direct access to the surface. Acoustic engineering is another essential element. Underground spaces can easily amplify noise or feel unnaturally silent. To create a comfortable aural environment, architects install sound-absorbing materials, ambient nature soundscapes, and advanced noise control systems. These ensure that living spaces are peaceful, harmonious, and free from echoing or mechanical noise. Spatial design also emphasizes open-to-stall ceilings, curved walkways, and multi-level communal areas prevent feelings of confinement. Interactive digital walls can display natural scenery, city views, or calming environments, creating the illusion of expansive space. Smart lighting adjusts brightness and color temperature to support mood, productivity, and circadian rhythm. By combining visual, acoustic, and biophilic design elements, underground cities can become vibrant, welcoming environments that feel just as natural as surface dwellings. These innovations ensure that subterranean living remains not only functional but emotionally uplifting. Beyond the blueprints, real-world underground projects. While futuristic underground megacities may seem like science fiction, the foundations for them are already being built around the world. Many nations are exploring subterranean development to address overcrowding, climate vulnerability, transportation needs, and land scarcity. Cities such as Singapore, Helsinki, Tokyo, Montreal, and Beijing are investing heavily in underground districts, logistics tunnels, data vaults, shopping complexes, and energy storage systems. These real-world projects showcase how underground infrastructure can operate efficiently while reducing surface congestion and protecting valuable green spaces. They also reveal the level of innovation involved: advanced materials, energy-saving systems, and automated construction technologies. The global push toward underground urbanism demonstrates that humanity is already preparing for deeper, larger, and more sophisticated subterranean living. This section highlights the ambitious projects already underway, the technological breakthroughs supporting them, and the economic and societal implications of transforming the space beneath our feet into functional city extensions. Highlighting ambitious, ongoing underground city concepts and early-stage construction initiatives globally. Around the world, several groundbreaking underground projects are laying the groundwork for future subterranean megacities. One of the most notable examples is Helsinki's underground city master plan, which incorporates hundreds of interconnected facilities built within excavated bedrock. This includes shopping areas, sports halls, power plants, data centers, and even emergency shelters, all concealed beneath the surface. Singapore is another global leader, developing deep underground oil storage caverns, research centers, and plans for underground science parks to save precious land. Montreal's Réseau, one of the world's largest underground pedestrian networks, stretches for over 30 kilometers, linking shopping centers, offices, and transit hubs, proving that underground mobility can enhance urban efficiency. In China, cities like Chongqing and Beijing are experimenting with multi-level underground complexes that integrate malls, subway systems, and emergency bunkers into dense urban environments. Japan has been exploring underground floodwater diversion tunnels such as the Metropolitan Area Outer Underground Discharge Channel, showcasing how subterranean engineering can manage extreme climate risks. Meanwhile, Middle Eastern nations have proposed futuristic underground districts designed to combat desert heat and optimize land use. These initiatives illustrate that underground development is no longer a theoretical idea but a rapidly evolving engineering frontier. With ongoing research, improved geological surveying, and advanced construction technologies, cities are steadily transitioning toward deeper and more expansive underground infrastructure. These global projects serve as early prototypes for tomorrow's full-scale subterranean cities. showcasing breakthroughs in material science, self-healing concrete, and transparent aluminium for structural integrity. Material science innovations are essential for building safe, durable, and sustainable underground megastructures. One of the most transformative materials is self-healing concrete, a special composite embedded with bacteria, microcapsules, or mineral agents that automatically seal cracks when exposed to moisture. This significantly increases structural longevity, especially in environments prone to water infiltration or high ground pressure. Self-healing materials reduce maintenance costs and improve safety by preventing minor fractures from expanding into major structural issues. Another remarkable innovation is transparent aluminium, a ceramic-like material known for its exceptional strength, scratch resistance, and clarity. While still expensive and used primarily for specialized applications, transparent aluminium could eventually serve as protective windows, observation panels, or light tunnels in underground spaces. Its ability to withstand extreme pressure makes it ideal for deep earth environments. Engineers are also experimenting with fiber-reinforced polymers, ultra-high-performance concrete UHPC, and graphene-enhanced materials to increase the structural resilience of underground chambers. These advanced materials offer superior durability, reduced thickness requirements, and greater resistance to corrosion and chemical attacks. Additionally, new waterproofing membranes, thermal-resistant coatings, and smart structural sensors are transforming the way underground environments are maintained. Embedded sensors can continuously monitor temperature, moisture levels, stress distribution, and crack formation, sending real-time data to engineers for proactive repairs. Together, these breakthroughs in materials science are redefining the safety and longevity of subterranean construction. They enable larger caverns, deeper structures, and innovative architectures that were previously impossible. The economic and societal impact of developing these monumental underground havens. The economic and societal implications of underground megacities are profound. On the economic side, developing underground spaces opens vast new real estate opportunities without expanding urban footprints. This can dramatically reduce land acquisition costs, protect natural landscapes, and promote sustainable urban growth. Major industries, transportation, logistics, data storage, energy, and retail stand to benefit from climate-protected, secure underground environments that minimize disruptions from extreme weather. Construction sectors will also see growth due to demand for advanced excavation technologies, high-performance materials, and long-term maintenance systems. Societally, underground developments can reshape how cities function. By relocating heavy traffic corridors, industrial facilities, or utility networks below ground, surface areas can be repurposed into parks, pedestrian zones, and green public spaces, improving urban quality of life. Subterranean spaces offer enhanced safety from natural disasters, providing secure shelters during storms, heat waves, or conflicts. They can also support population growth without overcrowding surface infrastructure. However, the shift underground also raises questions about accessibility, affordability, and long-term social integration. Ensuring that subterranean spaces are welcoming, psychologically comfortable, and equitably accessible is essential to avoid socioeconomic divides. With thoughtful planning, underground cities can become inclusive hubs that combine economic resilience with environmental sustainability. Ultimately, these developments have the potential to transform metropolitan living, setting new standards for safety, efficiency, and sustainability. The future is down, a look ahead. As cities around the world confront rising populations, climate change, and land scarcity, underground urbanism is emerging as a promising frontier for future development. The technologies and engineering breakthroughs being developed today hint at a future where subterranean cities are not just supplementary infrastructure, but full-fledged urban environments. By 2050, underground districts may integrate transportation, agriculture, housing, utilities, and recreation into deeply layered, self-sustaining ecosystems. Advanced automation, renewable energy systems, and intelligent monitoring networks will ensure these underground megastructures operate efficiently and safely. The future of subterranean living will depend not only on engineering, but also on ethical planning, inclusive policies, and sustainable governance. This section explores how underground cities might evolve over the next few decades, what innovations will shape them, and how humanity can responsibly embrace this new frontier beneath the Earth's surface. Speculating on the next generation of underground urban planning and what a truly self-sufficient subterranean city might look like by 2050. By 2050, underground cities could evolve into highly integrated, multi-layered environments designed to function with minimal dependence on the surface world. Future underground planning will revolve around complete self-sufficiency, producing food, recycling water, generating energy, and supporting healthy communities entirely below ground. Underground megastructures may be built in vertical layers, with transportation tunnels forming the upper levels, residential and commercial districts in the mid-layers, and deep utility networks, farms, and data hubs occupying the lowest levels. Smart infrastructure will use AI-driven monitoring systems to continuously assess structural stability, optimize resource usage, and manage environmental conditions across vast underground territories. Renewable energy sources like geothermal power, underground solar collectors, and waste-to-energy reactors will help maintain energy autonomy. Urban farms using next-generation hydroponics and bioreactors may produce everything from vegetables to cultured proteins, ensuring year-round food supply. Autonomous vehicles and magnetic levitation pods will transport people efficiently through underground corridors. Public spaces will be enriched with digital parks, simulated natural environments, and immersive lighting that shifts with virtual weather patterns. Environmental envelopes will maintain ideal air quality, humidity, and temperature using self-regulating ventilation systems. Future underground cities will prioritize sustainability, circular resource cycles, and human-centered design to create communities that feel natural and comfortable. By mid-century, subterranean cities may become a crucial component of global urban resilience, offering secure, climate-proof environments capable of supporting millions. Addressing the ethical considerations and global governance required for these massive infrastructure projects. The rise of underground megacities introduces complex ethical and governance challenges that must be addressed to ensure equitable and responsible development. One of the primary concerns is accessibility. Without proper regulation, underground infrastructures could become exclusive zones benefiting only wealthy populations or privately owned enterprises. Governments must ensure that subterranean spaces remain public assets, designed for inclusive access and affordable living. Environmental justice is another critical issue. Excavation on such massive scales can impact groundwater flow, ecosystems, and geological stability. Transparent environmental assessments and strict monitoring must guide all stages of development. Global governance frameworks may be needed to regulate deep earth construction, similar to policies that govern international waters or outer space. Ethical considerations also include labor rights, ensuring safe working conditions for construction teams who operate in hazardous underground environments. Privacy concerns may arise from the extensive sensor networks required to monitor air quality, structural integrity, and population movement. Clear guidelines must define how data is collected, stored, and protected. Social cohesion is equally important. Planners must avoid creating isolated underground societies disconnected from surface communities. Cultural needs, mental health support, and community-centered public spaces must be integral to planning. Ultimately, ethical governance ensures that underground cities evolve not as dystopian refuges, but as sustainable, inclusive environments guided by transparency, fairness, and responsibility. A final call to consider the incredible ingenuity and resilience of humanity in facing future challenges. Humanity has always adapted to challenges with innovation, creativity, and determination. As climate pressures intensify and urban populations surge, underground cities represent the next chapter in our long history of engineering resilience. From carving early cave shelters to constructing modern metro systems and data vaults, we have continually transformed the Earth to meet our needs. The vision of vast subterranean cities symbolizes not just technological advancement, but human adaptability, our ability to imagine possibilities beneath the surface and bring them to life through science and engineering. These underground environments remind us that solutions to the world's most pressing challenges often lie in rethinking how we use space, resources, and technology. As we envision homes, farms, transit systems, and green corridors deep underground, we are also redefining the future of civilization itself. The courage to explore unfamiliar frontiers, whether in outer space or beneath the Earth, reflects humanity's unbreakable spirit. The journey towards subterranean megacities is more than an engineering pursuit. It is a testament to our collective resilience in the face of environmental uncertainty, urban pressures, and global transformation. As we move forward, embracing innovation with responsibility, we must celebrate the teams of engineers, planners, architects, scientists, and visionaries working to design a safer, smarter, and more sustainable future. Below the surface lies not darkness, but opportunity, progress, and the next great chapter in human ingenuity. Thank you for watching Civil Engineering Edge. Underground cities may sound futuristic, but the engineering behind them is advancing faster than ever. As we face climate change, urban crowding, and land shortages, subterranean megastructures might soon become a real solution. If you found this exploration inspiring and want more deep dive videos on civil engineering, construction technology, and future infrastructure, don't forget to like, share, and subscribe. Your support helps us bring high-quality engineering content to learners across the world. Until next time, stay curious, stay passionate, and keep building the future one innovation at a time.